Hello, hello, and welcome to May's Comet Watch. Slight change here. We're doing another Zoom meeting that we're just going to stick up on YouTube, and everybody should be happy. Yes, you can. This is Nicky Vets live,
and Mary McIntyre live.
I'm Neil Norman, video free.
So as always, we'll start with the latest discoveries. So March 29th, PANSTARRS reports a Kreutzgruppe comet in real-time C3 images.
And March the 30th, Warchop Bloomplod reports 2 Kreutzgruppe comets in real-time C3 images.
April the 1st, and Rafael Biros reports a Kreutzgruppe comet in real-time C2 images.
April the 2nd, Warchop Bloomplod reports a Kreutzgruppe comet in real-time C3 images.
And on April the 2nd again, Masanori Yuchina reports 2 Kreutzgruppe comets in delayed C2 images.
April the 7th, and cometary activity confirmed in 2019 U5.
April the 7th again, PANSTARRS reports a Kreutzgruppe comet in real-time C3 images.
And another on April the 7th, Simon Liwu reports a Kreutzgruppe comet in real-time C2 images.
On April the 8th, Simon Liwu reports a Kreutzgruppe comet in real-time C2 images.
On April the 10th, Warchop Bloomplod reports a Kreutzgruppe comet in real-time C3 images.
And April the 11th, Warchop Bloomplod reports a Kreutzgruppe comet in real-time C3 images.
April the 13th, and he went for the hat trick. Warchop Bloomplod reports a Kreutzgruppe comet in real-time C2 images.
April the 13th again, Simon Liwu reports a Kreutzgruppe comet in real-time C3 images.
And on April the 14th, Piyuan Sun reports a Kreutzgruppe comet in real-time C3 images.
April the 14th, and Masanori Yuchina reports a Kreutzgruppe comet in real-time C2 images.
April the 15th, Masanori Yuchina reports a Kreutzgruppe comet in real-time C2 images.
And April the 16th, another hat trick, Masanori Yuchina reports a Kreutzgruppe comet in real-time C2 images.
April the 17th, and Warchop Bloomplod reports a Kreutzgruppe comet in real-time C2 images.
April the 18th, Simon Liwu reports a Kreutzgruppe comet in real-time C2 images.
And April the 20th, Warchop Bloomplod reports a Kreutzgruppe comet in real-time C2 images. Sorry, I should be able to say his name by now.
I know. 20th of April, Simon Liwu reports a Kreutzgruppe comet in real-time C2 images.
April the 21st, Warchop Bloomplod reports a Kreutzgruppe comet in real-time C3 images.
And April the 21st again, Simon Liwu reports a Kreutzgruppe comet in real-time C2 images.
Lots of hat tricks today. April the 24th, Warchop Bloomplod reports two Kreutzgruppe comets, in real-time C2 images.
April the 27th, Peter Barrett reports a non-group comet in archival C2 images.
And April the 27th, discovery of a 2021 F1 reported.
28th of April, discovery of A/2021 E2 reported.
And on 20th of April, this was updated. Okay, if there's been no recent updates, try the German Comet Group or Seiichi Yoshida's page for information, or the Liga Iberoamericana de Astronomia for observations. So we'll move on to current comet magnetism, the observable region. 2020 R for Atlas 8.5, steady 65 degrees north to 70 degrees south. It's best in the morning and last visually observed April 2021.
Then we have 10P Temple, that is currently mag 10.5 and steady. It's at poor elongation at the moment, last visually observed in April 2021.
Next, we have 2021 D1 Swan, magnitude 11, but now fading, 55 degrees north to 40 degrees north, early evening object, last reported in April 21.
2020 T2 Palomar, 11.5, bright, 70 degrees north to 30 degrees south. It's an all-night, it's an all-nighter really. Last visually observed 2021 April.
And then we have 7P Pons Winnock, that is currently 12.5 question mark, that is brightening, observable 70 degrees north to 65 south, that is best viewed in the morning, not yet visually observed.
Next is 2019 N1 Atlas, magnitude 12.5, now fading 20 degrees south to 80 degrees south, best viewed in the evening, and last reported visually in February.
Okay, 2019 L3 Atlas, 13th magnitude, bright, 70 degrees north to 35 degrees north. It's an evening object. Last visually observed April 2021.
Then we have 29P Schwarzmann-Wachmann, that is Mag 13 question mark. Of course, that varies. Currently at poor elongation though, and not visually observed since January 2021.
Oh, beautiful pronunciation. And finally, we have 2019 T4 Atlas, magnitude 14 and brightening, 25 degrees north to 80 degrees south, best viewed in the evening, and is yet to be observed visually.
Okay, that's the current comet magnitudes and observable region. Obviously, this is usually updated at the beginning of each month. It may be updated more frequently for brighter comets. The last partial update, of course, was April 17th. My thanks to Nick James and Jonathan Shanklin for this excellent page. One good piece of information for you, 2020 R4 is now a binocular stroke telescopic object, and UK observers can now see it in the late evening sky. It is near its brightest, and it will begin to fade quite rapidly as its distance from the Earth and the Sun is increasing. And on that note, that's the shipping forecast for comets completed, and our guest has joined us. So would our guest like to introduce himself?
Hello, I'm Dave Jewett. What else do you want to know?
Welcome to CometWatch.
Thank you.
Okay, actually, this is unusual for us because normally we use Skype, but sometimes we now that I have a Zoom account, this is great fun because people can actually see us. Or they can see all of us apart from Neil, who keeps hiding.
I last used Skype like years ago. And it was kind of, yeah, so I much prefer this. Yeah.
Anyway. I'm more familiar with Zoom as well.
It's last year, yeah.
Well, it's great to have you. And for people who don't know, you're actually a Brit in the US.
Yeah, that's true. Yeah. And, you know, I was thinking the other day, why am I interested in comets? One of the reasons is, I think, that, you know, I grew up in like Enfield in North London. And I always tried to see comets from Enfield. I never saw a damn comet. I never saw one. So I think the fact that I can see them is like a big thing for me. Even though I'm getting old, it's still a big thing.
Oh yes, and I think the only one we have that's everybody's going to be chasing is 2020 R4, which is a binocular or telescopic object. But you need to be outside of London, unfortunately. I know that some of the Baker Street irregulars may be listening to the podcast. I'm going to wish you the best of luck, guys, since you observe from the centre of London. But great, good luck. You might get it. So anyway, let's get this kicked off. So this is actually the beginning of the month show, really. We were supposed to have recorded yesterday, and I do apologise for having to shift the show to today. But unfortunately, work caused a few issues for me. So one of those things. Would you like to tell us a bit about your career and how you got started, David?
I can. So as I said, I grew up in North London. I was interested in the sky from when I was about 7. So, you know, from Enfield, I saw a bunch of meteors crossing the sky. I forget how many, it was like 10 or something in a very short period of time. And I went home and asked my mother, what did I just see? And she said, oh, they're shooting stars. They're shooting stars, David. And I thought, that's kind of weird. How can a star shoot? Like, what does that mean? So I started to ask more questions about the sky. And I realized that, you know, neither my mother nor anybody in my family knew anything about the sky. And so that was kind of cool. I thought, great, I can ask questions that they don't know the answer to. So they went from being great sources of knowledge about everything to being people who didn't really know things about the natural world. And I thought that was great. Anyway, so that's the beginning of astronomy for me. And I got a little tiny telescope. It was a 40 millimeter refractor. I used to look at everything with that. And I just thought it was completely astonishing that I could see the moon, you know, in great detail, and the rings of Saturn and the satellites of Jupiter, all the things that are good to look at. I could see from Enfield, you know, and it's the worst sky in the world, but I could see a lot of stuff, and I thought that was just fantastic. So then I got interested in science in general, and I got interested in physics, and then eventually, somehow I found out that there's a thing called a university, and I could go to a university, which nobody in my family ever did, or knew anything about, actually. And I went to this university college in London, which turns out to have been a really excellent thing for me. So they had a really, really strong undergrad program at that time, which was like 100 years ago. And then from there, just by chance, I met this random, well, he wasn't random. He was a professor there, an American who was employed at University College London called Mike Dwarfs, who mentioned that, you know, there's this place called Caltech in California, which I never heard of, some university thing. I didn't know anything about the US at that time. It was like everybody was amazingly ignorant back then because lack of internet is just much, much harder to get information. But then I found out that Caltech, you know, was connected somehow to JPL, which I'd heard of because of the space program, and connected to Palomar, which I'd heard of because I'm reading all these books with pictures from Palomar, and it's all fantastic. So I thought that might be a really cool place. Maybe I should go there. So I went there and I became a grad student. And then after that, I was a professor at MIT. Then I was a professor in Hawaii, which has basically the best access to telescopes anywhere. And then 10 years ago, I came to UCLA, which is where I am now in Los Angeles. That's my whole life in a nutshell.
You've worked on a lot of stuff as well throughout your career, different kind of astronomical objects, but I think it's lovely that you came back to comets having seen what was probably a meteor shower caused by one.
That's really true. Yeah, it's kind of circular. Yeah. And in fact, you know, the meteors in that shower, I forget which one it was, but indeed they were from a short period comet that had its origin in what we now call the Kuiper Belt, which was unknown at that time. And so the whole thing really is kind of nice. Yeah.
Now, I know that you're actually one of the first people to, after 5 years of searching, to actually, let me get this right, you discovered the first Kuiper Belt object other than Pluto and Charon, being 15760 Albion with Jane X. Lu, correct?
Yeah, yeah, all true. Yeah.
What was that like, actually finding an object like that apart from Pluto?
Well, it was good because there was no Kuiper Belt, right? So that was not a thing. So when we started, at least, it was not a thing. And we were not looking for the Kuiper Belt because it was not a thing. We were just looking for anything beyond Saturn. So at that time, you know, there was just the planets and then nothing. Whereas in the inner solar system, there are lots of asteroids and comets and all sorts of things. So the question was, why would the outer solar system be absolutely empty of stuff and the inner solar system has lots and lots of small bodies in it? That's the question that we're trying to answer. And we tried a whole bunch of things, as you said, for years without success. And so finding the first one was really very nice. And we didn't find anything beyond Saturn. I thought it'd be easy to find something beyond Saturn because it's closer. But there is nothing basically beyond Saturn, beyond Uranus, beyond Neptune. It starts to get interesting. Once you get outside of the domain of the giant planets, then you find this ring of material, the Kuiper Belt, out there, which turns out to have billions of objects in it, of which about 3,000 have been seen so far. So yeah, we found the first one in '92. Then over the next few years, we found another 40 or 50. I kind of don't know exactly how many. And then other people joined in, and we're up to 3,000 at the present time. So it was great because we've been looking for a long time. And after a while, you think, maybe this is a waste of time. But we were ready to interpret it straight away. So we found this moving object. We're up at the summit of Mauna Kea, 4,000 meters altitude, is about 14,000 feet. We're reading out a CCD, into a computer. CCD at that time was the biggest operational CCD is a 2000 by 2000. Nowadays is nothing, but 2000 by 2000 CCD. And the computer, I remember, was this horrible computer that we had to carry up there because there was no equivalently powerful computer. And that computer was some Sun thing, a Sun 360 or some horrible thing that doesn't exist anymore. It was like computers don't sweat, but it was basically sweating to read out the CCD. It was like, oh my God, there's so many pixels. And it was just agonizing to do to carry this computer up. And there's a big CRT monitor. There were no flat panels, you know, and every time you go up to the top, there's a chance of breaking it because of the vibration in the car, and the low pressure at the summit is a pain. Everything is just really, really painful. But we did that a lot. And when we got the first object, immediately we knew how to estimate the distance from the speed. And then we measured the brightness. And then we're able to combine the distance and the brightness to estimate how big it was. And then we knew that we'd looked at, you know, some tiny fraction of the sky, I forget, but a very, very small part of the sky. So then we could extrapolate and say, well, how many must there be if we see one in this little tiny area? How many would we see if we looked all the way around the ecliptic in the solar system? And the answer was thousands. So literally within the course of 1 hour, we went from, no, this is hopeless, there's nothing, to, my God, there's something there, to, wow, it's 200 kilometers across, and it's 40 something AUs away. You know, Neptune was 30, still is 30, and there's thousands of them. So we immediately knew there was a huge number of objects in the outer solar system, not previously seen because nobody had really gone faint enough and looked in the right way to see moving objects. People had gone fainter on that background stuff, those stars and galaxies, you know, but people had not done a good job looking for anything moving.
Now,
so we were
I also know that you were actually the first astronomer to recover Halley's Comet back in '82 using the Hale telescope and a very early CCD camera.
Yep.
What
do you actually pronounce it Halley?
Well, seems to be, the jury says it's either Halley or Hawley.
Halley.
Yeah, what else could there be? Oh, Haley.
Yeah.
Haley.
Yeah.
Halley, yeah.
Haley is what I say.
But from what I understand, reading of the diarist of the Times, who, like Hawley was a friend of Newton's, it seems to be that either Halley or Hawley was accepted as being correct. So it's amazing what you find out listening to Patrick Moore and Chris Lintott.
Yes. Despite that, I'm going to stick to Haley. Okay.
Yes.
And that must have been pretty exciting to recover.
Well, that was, so I was a grad student. This was starting in, I think, 1980. So I was a grad student, 79 or something. But I realized that when I was at Caltech, I could, in fact, use the telescopes at Palomar. So before I went there, I imagined this place is like such a cathedral to astronomy. It's, you know, it's the biggest telescope in the world, 5-meter, 200-inch telescope. You know, there's no way I could ever get close to that thing. Nobody's ever going to let me do anything with that. And it's true, in my department, nobody was using it. It was like, well, we're just doing spacecraft stuff. So I thought, this is ridiculous. So I found ways to get observing time on Palomar. And I started to do measurements of different things. But I had a great thing going for me, which was my advisor is this guy, Jim Westfall, was building the first CCD camera to be launched in the future on the Space Telescope. So there was a prototype built by him and a person called Jim Gunn into a camera called PFUI, P-F-U-E-I. That was the world's best CCD camera at that time. And I got to just mess around with that camera on mostly the 60-inch at Palomar, but sometimes I would get some time through a backdoor route on the 200-inch. And that was great. So one of the things I did, I mean, I wrote a bunch of papers and stuff about data from Palomar, but one of the things that seemed kind of cool would be to look for comet Halley, or Hawley on its way to perihelion. So starting in 1980, I began to look for that. And, you know, in 1980, nothing at all. And then 1981, nothing at all. But again, I kept trying with that. And eventually that was successful in 1982, 4 years before perihelion. So at that time, Comet H was the faintest thing ever seen in the solar system. It was 24th mag. Now nowadays, 24th mag, people go,
Yeah.
Yeah.
But back then, that was astonishingly faint for anything ever seen in the solar system. And so with that, I was able to get the size of the nucleus. I said something about the activity state. It was not active at that time, and a bunch of other things. It was quite cool. What I didn't know is that other people were looking, again, because of this communication problem. Today, everybody communicates really well. There's just a huge flood of information going around on this internet thing. But with no internet, no way. So people could be doing the same thing in different places and you would never know. And indeed, that was the case. So there was a guy called Mike Belton at the National Observatory in Tucson, in Arizona, who was using their telescope, which was a 4 meter, basically almost the same size, 4 meter, 5 meter, who had been trying as well to find Comet Halley. So but he knew somehow about me. So in his mind, it was a competition. But in my mind, I didn't know about that until after the fact. Yeah. So, you know, it became more exciting afterwards, even than it was before. So that was good. And the whole thing, in retrospect, was kind of practice for finding the Kuiper belt, because the technique that I used for finding Halley, basically take multiple images and then compare them on a computer, is the same as was used for the Kuiper belt, and still is used for the Kuiper belt. It's the same basic idea. So perhaps, you know, getting all psychological, perhaps the success with Comet Halley was a little bit of a trigger for trying to find stuff in the outer solar system that might be as faint or even fainter.
It's all such cutting edge stuff as well. I mean, we, like you say, we just know this stuff is there now, but I can't imagine how exciting it was. And it's a bit like with exoplanets, I know you've been involved with as well. The minute you find one, you know that they're everywhere. And it must have been the same finding that first object. And
because this really is kind of funny, but there are many examples of this through science, as you probably know, that, you know, people always think that detection is all that it takes. That you just have to detect something and then you got it. But actually, it turns out that it's not true. You need detection, but you also need perception. You also need to be able to perceive the thing you've detected. So Kuiper belt is an example of that. We detected and perceived 1992 QB1 Albion correctly in 1992, but Pluto was detected but not perceived correctly in 1930 by Clyde Tombaugh. But Pluto, of course, was not first detected by Clyde Tombaugh. It was detected long before, 30 years before. So people have gone back and found Pluto in the photographic record long before it was actually discovered by Clyde Tombaugh. Now people have gone back into the Palomar Sky Survey, which was ongoing in 1950, and looked for some of the brighter Kuiper belt objects that were found in the 1990s and 2000s, and they find them. So the Kuiper belt could have been found in the 1950s if people were looking at detected objects in the existing data. I mean, they were just sitting there unnoticed from the 1950s. And then the same story goes for Neptune. I forget when Neptune was discovered, but it's 1842 or something like that. You know, yeah, I just can't remember when it was discovered. But
1846, yeah.
Okay, 46, 4 years off.
Yeah, 4 years.
But it was first detected in 1610 by Galileo, because he drew it, right? As it was going behind Jupiter, he was drawing the satellites. Neptune went behind. So in principle, it could have been discovered in 1610. So there's always this tension between detection on the one hand and perception on the other hand. And then once you've done that, once you've realized that there is a thing to detect, then it just becomes magically easy. It shouldn't be like this, but it just becomes magically easy. So the subsequent Kuiper Belt objects that we found, were much less of a thrill than the first one because they were not such a big surprise, because we knew that there was something there to be discovered. Whereas before we found the first one, we didn't know that there was something there to be discovered. We knew about Pluto, but at that time, Pluto was this planet. It was this weird planet. So it's just it's like breaking through some kind of a weird psychological barrier. And then it became so ridiculous that as the years went by, and even to this day, when I go observing, I find Kuiper Belt objects moving in the background of the thing that I'm looking at. Yeah. And I can't even be bothered to measure them or make a record of them. It's just like, another one,
Yeah.
So it's really, it's a little bit sad, but I just don't have the interest or the energy to follow them all up because it's kind of been there, done that thing. So
I've got like that with satellites. I used to be quite excited by certain ones. Now I'm like, oh God, get out of my picture.
There's so many of them. Yeah. So anyway, the discovery, is partly detection and it's partly perception, for sure.
And I can't imagine how exciting it was to actually have picked up something that faint magnitude when you recovered Comet Halley, though. I mean, to know that you could actually see something that faint with your equipment must have been like, wow, what else are we going to find now?
Well, no, strangely, I didn't put it together. So
okay.
In 1982, that my thought process ended with, I found Comet Halley. That's where it ended. So the idea of going on a search for anything was not an idea in 1982. Certainly not for me. I don't think for anybody else. So I didn't do anything about that for several years. So I started with Jane Lou, started that search in like 86. So again, 4 years later. Yeah. So all this stuff seems obvious and automatic, in retrospect. But in reality, nothing is obvious, right? So it's all, figure it out as you go along.
Now, I know that one of your areas of interest is actually two particular comets, one of which I've actually imaged, which was C2017 K2, and our old friend 2I Borisov.
Yeah. Is that your friend?
Put it this way, I did make an attempt to image it. I didn't succeed, but I made the attempt.
Okay. I'm sure Comet Borisov would be happy about that. Yeah. So about those. Hello?
Sorry, yeah, I'm still here.
Yeah.
A bit of a cutout. Did you want to talk about those?
Please.
So K2, 2017 K2, is this comet that was discovered in 2017 at a very large heliocentric distance. So it was discovered at 17 AUs from the sun and was already pretty bright by then. So that's interesting because, if you look at the classical model of the comet nucleus, comet is this mixture of water and dirt and things. Water is not volatile really beyond the orbit of Jupiter. So out to about 5 AU, you can have some weak sublimation of material and you can expect a coma and a tail. But beyond 5 AU, it's too cold. And water is more like a mineral, it's like a rock. So why would a comet be active at 17 AU is the immediate question that comes to mind. But then we went back into the archive. So my graduate student, Manto Hui, who's now gone to Macau, looked back in the archive and found an image of K2 from several years previous at 23 AU, 23 AUs from the sun. Wow. So it was active even at 23. So beyond the orbit of Uranus, which is at 20, roughly. So that's pretty remarkable. So that has triggered a bunch of measurements. So I've written some proposals to get time from Space Telescope, and those proposals are continuing. So it's given us the opportunity to study the development in the activity of a comet from tremendous distance, all the way in, hopefully, towards perihelion, which is going to be at 1.8 AU. Mars is at 1.6 at the end of 2022, next year. And it's not really been done before. So the idea is that we could see how the activity in K2 develops as a function of the distance from the sun. And because we're looking at a regime or a realm that's not really been probed before, we'll probably see some new things. And we'll probably get a better understanding of how comets work in general. So, the classic problem with comets is that, if you find them out there at 6 AU or something like that, and they're brightening, and then you extrapolate that in to perihelion, it's going to be the comet of the it's going to be the comet of the century. So almost, there are dozens of comets of the century every decade, as far as I can tell, because it turns out our ability to extrapolate, and predict how bright the comet is going to get is very, very poor. We don't really have the handle on how to do that. So the hope is that by studying K2, we'll get a better idea of what's going on. What are the physical processes that are occurring in the comet that make it get brighter as it comes closer to the sun? And then when it goes out the other side, we'll watch it get fainter as well. But it's just doing it over this, basically most of the planetary region of the solar system. In fact, I just, like the most recent, almost the most recent data I've analyzed that, and I just wrote a paper about that. Looks like the activity actually began at 35 AU, which is astonishing. Wow. It's a Kuiper belt.
Wow.
So if it's doing it at 35, there must be other ones doing it at 35 as well. They haven't been noticed for whatever reason, but maybe now we can find some more. And why would they do that? We don't know, but the suspicion is it's some super volatile material, maybe carbon monoxide, very nasty, but it's abundant in comets, or carbon dioxide is not really sufficient at 35 AU, but could kick in at, say, 20 AU. So there are a bunch of possible ices that could be sublimating at large distance. And then there are just other physical processes, which nobody really ever thought about much for comets, that could operate at very large distances and very low temperatures, and could drive some activity from the comet. So again, it's an area where very little is known because there are very few observations. Essentially, it's K2. I mean, K2 is it. And so the prospects for finding out cool new things are pretty high. One thing that we already did find out is, and I don't want to go on about K2 in case that's too boring, right? I find it very interesting.
No, go.
Okay, well, if you guys are like pre-selected comet nuts, that's a good thing. So the standard view of comets is that the dust particles are very small. And in fact, near the sun, they are very small. They're like a micron, thousandth of a millimeter, very, very tiny. But we measured the size of the particles in K2 out at large distances, and they're not a micron, they're a millimeter, basically. They're huge, they're like grains of sand. That in itself is very, very strange. And it means that the process, whatever the process driving the activity is, can eject millimeter-sized particles from the nucleus, but there are not a lot of micron-sized particles. So somehow the small ones are not getting out. So again, that's not fully understood, but a possible mechanism is that, dust is sticky. So if you wipe your finger on you can't see it, but if you wipe your finger on the desk and pick up some dust, it sticks to your finger if it's small. And if it's too big, it doesn't stick to your finger. So the very small particles are affected by cohesive forces called van der Waals forces, but that doesn't matter. And so those sticky forces could be binding the small particles in K2 so they can't get out. So you've got the gas flowing this way. The gas is going up really fast, probably, hundreds of meters per second is flowing out. And so it exerts a drag force that's trying to lift the particle up. But there's a sticky force trying to pull it down. And the balance for the small particles is in favor of the sticky force. So the small ones just can't get off the surface, but the big ones apparently can. So we have this strange, again, quite strange result. You'd expect it to be the other way around, because the gas flow at 1520 AU is very weak. You might think that it would be able to lift the small ones and would not be able to lift the big ones. Whereas when the comet comes close to the sun, it can lift everything because the wind blowing up from the nucleus is very strong. But in fact, it can only lift the big ones a large distance from the sun. And that is backwards from what we thought, but pretty interesting. And then when we know the particle size, we can estimate how quickly the comet is losing mass. And it's right now, it's about 7 AUs from the sun, I think maybe 6. It's losing hundreds of kilograms per second in dust particles in the comet. And that's a pretty big rate too. I mean, that's comparable to 67P Churyumov-Gerasimenko at perihelion, but it's way, way out. So this is a very, very interesting, very active comet. And there's a lot of promise for the future. Am I going to predict how bright it's going to get? No, because I'm not that dumb.
Well, obviously it's going to light up our sky, because that's what the press say every time there's a comet here in the
You
UK.
might get radiation burns on that side of your face.
Foil hats out.
Yep. It could be spectacular.
I know that when I imaged it back in August of last year, I had to do astrometry, which I'm not very good at. I'm the first person to admit it. That was the only way I could actually confirm, because it was a very faint smudge right in the center of the picture. But doing it that way, he said, yes, it's definitely the comet I was looking for. So I had to put a circle around it, because somebody said, well, where is it? I said, just enlarge the pictures, just inside that circle. And it's like, how far is that out? And I said, go look at Seiichi Yoshida's page. He'll tell you exactly how far it out, where it is. And they came back and says, wow. And just to think, this was done last year. It was done on a remote telescope. Very minimal processing from me. I think the most I did was the astrometry, but it was enough to say I could post a picture and say, this is K2. But I really enjoyed, it really made my day. Yes, there's a lot of brighter, easier to get comets that everybody goes for, but at that point it was very faint still, but we knew it was outgassing, and everybody wanted to get a picture of it. So it was good fun.
And it's hard to do astrometry
course,
when things are that faint as well. So well done.
I'm like the world's worst, astrometry person. I can't measure anything. I mean, I'm just hopeless at that. One thing about K2 is that when you look at it or get a good picture of it, you see that it's remarkably circular. Until recently, it had no tail. It was just a circular thing, like kind of a globular cluster coming in. It's just really, really freaky appearance. And that's because of the large particles. So you get the tail, right? Because radiation pressure blows particles away from the nucleus. But that radiation pressure is a function of the size. So the small particles are the ones that are most easily swept into a tail. But K2 doesn't have those small particles, just has these big things. And the big particles just come out and make this spherical cloud around the nucleus. And it's been spherical for most of the time since we first imaged it. Only recently has it got a tail.
I'm gonna have to go image it again.
We will.
No choice.
Do we know, David, how much of the nucleus is active? I read somewhere there was 2 jets confirmed that's been seen in data.
It's the comet now has asymmetry due to a tail, and has a little bit of asymmetry due to non-uniform outgassing from the nucleus. But no, we don't know what fraction of the surface is active. We don't even know how big the nucleus is, actually. So I set a limit using space telescope. The radius is less than 9 kilometers. But that's all I can say. I don't know. My guess
And the
would
good
be it's
thing
5
is,
kilometers radius. But I don't know. Yeah.
and the good thing is, because I looked at the eccentricity of the comet when I looked at the orbits, and I thought, oh, it's hyperbolic, but it's actually it's a returning comet, isn't it? It's only
Yeah.
going to be hyperbolic now because it was about 3 million years ago, so it has made a pass before at perihelion. So
Yeah. So yeah, it's not what they call a dynamically new comet. So it's not making its first pass into the solar system from the Oort cloud. That's where it comes from.
yeah,
And indeed, the current orbit period is about 3 million years, something like that. So it's been through. We don't really know the perihelion distance last time, but it was probably inside 10 AU. So it's probably active last time because it's active at an even larger distance this time. But not much is known about that. And yes, in the future, it will become hyperbolic. So the gravity of the planet's going to give it a little boost, and it's going to leave and never come back. But still, it's very, even though it's not dynamically new, so it's not a first arrival, it's very close to that. It may be making a second or third journey through the planetary region of the solar system. And also with 3 million year orbit period, it has no thermal memory of coming through before. In other words, any heat that it picked up at the previous perihelion has long since been lost.
Yeah.
And so any activity that we see now is due to heat that it's receiving now.
Yeah.
And so that's a very, very nice thing. If you want to interpret the data, that's a very convenient thing compared to a comet with a shorter period where you're not completely sure, is the activity caused by heating now, or is it caused by remnant, is it remnant activity from heat that's been conducted into the interior and then is slowly coming out again, as you might see for some short period comet, relatively short period comet. So it's really a good comet to look at. Very exciting. It's unique at the moment.
Yes.
Yeah. This is what I constantly try and get across to people who are non-astronomers whenever we look at comets like this, is it really is a kind of one-shot situation, and they all have their own story to tell and they're all unique, and it's so important that everybody is observing them and reporting those observations. Yeah,
I think so. I think, and in fact, probably a lot of members of the public, would be excited about comets if they could see a good one. That's what I think. But I think that somehow the hype and the media have sort of, created some trouble by advertising comets that don't turn out to be great. And so, that turns people off. People have a memory. Oh yeah, I was out there, half the night looking for this comet. I didn't see a thing. So that they get disappointed. Yeah, so a nice bright comet would be a really good thing. There was a huge surge, right, after Hale-Bopp, for example. Huge surge of public interest in comets, and Halley, for that matter, Halley as well.
That's it.
Well, last year I was kind of constantly getting everyone in the village to go out and look for Neowise, because for us in the Northern Hemisphere, that is like the best comet we've had in such a long time. And beginners were struggling to see it. And I was like, it's like literally there. I can see its tail sweeping up. And even with me like carefully using the plow, which everyone knows as a finder truck, people were emailing me saying we couldn't find it. I was like, oh my God. So I was guilty of it myself last year by getting very excited about Neowise. And
I mean, here, okay, so I'm living in Los Angeles. LA is probably worse than London, for sky conditions, because not only is the sky super bright, but the turbulence is super bad. So for telescope stuff, it's kind of, But we drove like a few miles north from here to a mountain on Mulholland Drive to see that comet. There were a bunch of people. It was like 20, 30 people. And they could see it, even though the sky is like ridiculously bright from all the scattered light from city, and city just goes off 100 miles. It's crazy. But you could see the comet, and people were genuinely excited to see the comet. You could see it naked eye, and you could see it very well with binoculars. So all the people who took the trouble to go out were extremely excited. It's a self-selected group at some level, but still. People were very, very interested in doing that.
Well, a lot of people are guilty of looking at typing on their phone that they can't see the comet, and that's because you've been staring at an LCD screen the entire time you've been out. So give yourself time to dark adapt, because it makes a world of difference.
Yeah. Although in LA, there's only so much dark adaptation you can do because it's not that dark.
Well, I know that the light pollution from LA at one point threatened Palomar. I know that there was a lot of concern about it affecting the James Lick telescope as well. I managed to get out there back in '85. Gosh, I'm showing my age now. And they actually had a star party, and basically they told you had to come up the mountain in daylight, nap in your car, and we'll all go down as a group afterwards. And they really mandated keep your spacings, keep your eyes on the road, and it was awesome. Not perhaps as good as Kielder up north is, or Brecon Beacons, but it was still dark enough you could actually get some really faint stuff. And they actually had the refractor in the Lick Observatory. So basically, I signed the book as a BAA member. So I said, well, if you come back tomorrow night, we're going to open the dome and you can use the refractor. Oh, I came back. Don't worry. that was an awesome piece of kit to use.
Yeah, I've never used that, but I know about it.
But that was an experience. I don't think that people can actually use it at the moment anymore, but it was something to treasure, really. But no comets, unfortunately, but definitely some planets and stuff. Made it all worthwhile, and it shows you what you can actually do. May not got the latest telescopes, but by gosh, it still works beautifully.
Yeah. I mean, another one nearby here is Mount Wilson, which used to be like, the place to be, but now the light pollution is mostly so bad you can't use it.
Yeah, I had enough problems in upstate New York when I was living out there. In fact, I used a million candle watt torch to shut down the streetlights temporarily, and it works.
For how long?
It gave me about 10 minutes of dark. So with a pair of 20 by 80 binoculars, you've got a chance of seeing something. But then about, I think the second night I tried it, I got a visit from the police, because somebody said, oh, someone was shooting the lights out. I said, not shooting them out. And I just says, oh, you're doing what we do. And he saw my huge torch. But so I got them looking through the binoculars, and they said, yeah, okay, we'll just tell our desk officers not to worry and let them get on with it.
Like Professor Dumbledore with his deluminator.
What a brilliant idea, Mary.
So what was the other comet that you mentioned? Was that another discovery?
To Iberoamericana, the interstellar interloper. Yes.
Yeah, I mean, I didn't discover that, as Borisov did that.
Sorry.
The other name is Borisov. No. So that is, as you know, is the second clearly established interstellar object passing through the solar system. In fact, is more distinct than the first one. So Oumuamua was on an orbit that was hyperbolic, so it's not gravitationally bound to the sun, but Borisov is just crazy hyperbolic. The eccentricity was 3 or something. So what that means is, at infinite distance from the sun, it still has a huge relative velocity. So if it's on a parabolic orbit, the speed at infinity is 0. So basically a parabola is what you get if you just drop something from infinity and it falls in towards the sun. It's traveling at some speed, even when it's far away from the sun. So it has its own velocity. It doesn't really care about the sun. It's just going to pass by.
Yeah.
And it answered a question that was raised by the first one, by One Eye Oumuamua. That question was, why is it so weird? So Oumuamua, everybody expected it to be a comet, but it didn't look like that. It didn't show a coma, didn't show a tail, it looked like an asteroid. But it didn't even look like a normal asteroid because it had a huge light curve. It had a huge rotational light curve. As you rotate the nucleus, you see it big side on, then like a pencil, like end side on and fat side on. So the light goes up and down like a sine curve. For an asteroid, that up and down from top to bottom is typically, 20, 30% difference, not more. But in the case of Oumuamua, it was a factor of 10 difference. It was 10 times brighter at its brightest than it was at its faintest, suggesting at first that it had the proportions of 10 to 1, which is a bit like the shape of a Saturn V booster. And it was also similar in size to a Saturn V rocket booster, which excited a lot of people briefly. Now, so the question is, why is that? Why is it the first object you find in this new population is just so strange and is so distinct from anything we've seen before? Are they all like that? Was the question on people's minds. So the second one answered that straight away. No, they're not all like that. So the second one looked like what we expected for the first one. It looked like a comet moving on a hyperbolic orbit. So it had a coma, had a little bit of a tail. It just looked exactly like almost any other comet that we'd seen in pictures. Raising other questions, well, why is it that we've got two objects and they're so different? What causes the difference? So are these actually two different families of bodies? Like there's a family of Oumuamua type things, and there's a family of Borisov type things, or is one an evolutionary state of the other? So for example, maybe Oumuamua started out looking like Borisov with a coma and tail, and then somehow it lost the volatiles. And so it's this largely devolatilized chunk of stuff passing through the solar system, and it doesn't have an obvious coma or a tail. Those are the kinds of questions that people are interested in. So lots of observations were taken of Borisov. I'm still analyzing mine, some of mine. I published many, but I have more to go. There, the nucleus, got the nucleus size, it's quite small. So the nucleus is not bigger than half a kilometer in radius. So a kilometer in diameter is the maximum. The smallest it could be is about half of that. So somewhere between half a kilometer and 1 kilometer in diameter. So it's not particularly big. It's outgassing a bunch of stuff. The outgassing was not symmetric, but that's normal for comets. It tends to throw stuff off towards the sun because it's hot on the day side of a comet, cold on the night side. So the ice is sublimating on the hot day side. So it projects material towards the sun. And then that exerts a reaction force on the nucleus. So the material goes that way, and the nucleus feels a push in the opposite direction that causes this non-gravitational acceleration, which again has been seen in comets for a long, long time, at least since the time of, before Whipple, actually, long before Whipple, 100 years probably. So we see that in Borisov, and it's completely unremarkable, it's normal. Other people measure the composition by looking at the spectrum. And they see that basically it's emitting the same materials that solar system comets emit, albeit with a bit more carbon monoxide than we see typically in solar system comets. So we've got these various measurements of Borisov, and now we're waiting for the third one. So it's going to be best of three. It's like, is the third one going to be like the first one or the second one or something else again? We don't know.
Probably something else again.
That would be great, of course.
I would.
So
now,
what we got, the main scientific thing that we've got from these interstellar objects, I think, so far, is the sheer number of them is ridiculous. So based on the first one, it was possible to estimate how many of them there are per cubic AU. So there's 0.1 of them in a cubic AU. So every 10 cubic AUs, it's like two and a bit by 2 and a bit by 2 and a bit AU. That's 10 cubic AUs. You've got one of these interstellar objects all through the solar system. So they're actually quite abundant. Inside the orbit of Neptune, there are 10,000 of them.
Wow.
Huge number.
Wow.
And we've only just seen that first one, the Oumuamua, the first inactive one. We only saw that because it came pretty close to the Earth and in a direction where PANSTARRS, the telescope in Hawaii, was looking. So in fact, that's how the density was, the number density was estimated from the PANSTARRS observing strategy. You know, which part of space you're looking at, you know, roughly the volume of space in which you could detect such an object. And so you can estimate how many objects there must be in that volume to give you a likelihood of finding one in a couple of years of operation. So it's 1 every 10 cubic AUs, 10,000 in the solar system, inside the orbit of Neptune. They take 10 years, because they're going so fast, 10 years to cross from one side of the solar system to the other. So if you got 10,000 objects and they each spend 10 years in the solar system, that means they're arriving at the rate of 1,000 per year, which means 3 every day. So we got three new ones coming in every day and 3 other ones leaving every day in steady state in this population. It's just totally ridiculous.
Yeah.
And totally unsuspected, you know, undetected and unsuspected until recently. Again, you know, I'm hoping it's a little bit of this detection perception thing that now people will be much more alert to the possibility of hyperbolic comets, hyperbolic objects, than in the past. And so we'll detect them more frequently, even with the existing technology. And you know, as the famous story about Borisov is that Borisov was not using some huge telescope.
No.
This Russian-Ukrainian guy with a telescope, I think it was about that big. I mean, it's not big, but it's not huge, not meters across. And he was just doing it for fun, looking off near the sun, and he found this comet. And he identified it as a moving object, as a comet, and reported it, but he had no idea that it was a hyperbolic object, and it turned out to be this fantastic discovery. So the first one is found by this survey, that telescope. The PANSTARRS thing is like $100 million thing, and the second one was found by this guy. I don't know how much he spent on his telescope, but it wasn't $100 million.
Definitely not. No.
Yeah.
Wow.
So that's really encouraging. That means that is confirmation there's a lot of this kind of thing to find out there if you're just looking. And my suspicion, I mean, I have no evidence for this, but still I have a suspicion, which is that in the past, hyperbolic comets were discovered. And, you know, the procedure is a little bit misty and a little bit murky, but people find a moving object and they report it, and they report astrometry if they could do the astrometry quickly. And it goes into this, at least in the US, it goes into this minor planet center, which has always been a little bit of the clouds of mist surrounding it. So I think that in the past, I'm just very suspicious that in the past, if an object came with an orbit that could only be fitted if the eccentricity was large compared to 1, either the software would reject it, or a human being who shall remain nameless at the minor planet center would reject it because it's impossible. You can't have that.
No.
I think there's been this bias against such objects. And the presumption would be, oh yeah, somebody screwed up with the astrometry. Yeah, we're just trying to fit bad astrometry, and you know, the E should be less than 1, and we're getting E of 1.5. That's nonsense. That can't be true. So forget it, you know. I think that's probably happened a bunch of times.
I'd agree with that totally. Is there did the comet go into outburst, or is there signs of fragmentation? Because there seems to be a bit of a debate about that. I think it was April this year, or sorry, last year.
Yeah, there was an outburst in March of last year, I think, from memory. And then HST images, I think like a month later, showed a fragment coming out. I put it in a paper, but I don't read my own papers much after so I have to go reread them to figure out what exactly happened. But I think it was about a month later, the fragment was detected. And then another fragment was detected a couple of months after that, again from Hubble Space Telescope, because you have this really fine resolution and you need that to see a faint object next to the brighter object and so on. So yeah, it's fragmenting. Now, it's not like a split in two. This thing about comets splitting is not, it doesn't give you the right picture. It's not the nucleus is cut in halves or something. It's a little thing comes out.
Yeah.
So I estimated the size of the fragment, and I think it was 5 or 10 meters or something out of a nucleus that's probably 500 meters across at least. So it's a tiny fraction of the total mass, maybe a millionth of the mass.
Yeah.
But it comes out, and there's a shower of dust that comes out with it because it's breaking off the surface. And so it was beginning a disintegration, but it did not actually disintegrate. The nucleus maintained its integrity, it just ejected a piece. And why it ejected a piece, we don't know. In general, we don't know why comets do that. But one idea is that they can spin up, so they lose mass, but they don't. It's like one of those fireworks, a Catherine wheel. They don't lose the mass symmetrically, and so the asymmetric mass can spin them up. And if they go up too fast, then centripetal forces just blow out material. That's one possibility. Or maybe it's just some pocket of gas, a super volatile gas under the surface, and the pressure grows and it just knocks out something from the nucleus or something like that. So again, that's what we see in comets generally. That's a very normal cometary process. Nothing too surprising about that, although it's kind of nice to see it in the case of Borisov. And that just reminds me, the last thing to say about Borisov or any of these interstellar objects is, once they're out, so they're ejected from some planetary system elsewhere, we don't know where and we don't know when. We'll never know where or when in general, I suspect. Once they're out, space is so big, the gaps between the stars are so huge that they will not come close to a star on the average for billions of years. So for Borisov, that's probably it. This is probably the first time it's come anywhere near any star. Happens to be the sun, so we're lucky. But it will go on probably for billions of years, never coming so close to another star, just because space is so empty. It's just ridiculously empty.
Oh, it's so lonely.
Really, yeah. Really.
After all the eyes on them for a short period of time, and that's it, they're on their own, off you go.
Yep, it's just crazy.
That's so interesting.
If you had an unlimited blank check and you had said you can do something, you can send a space probe to an object, what would you select?
If I could send a spacecraft to an object?
Yes.
Well, I wouldn't send a spacecraft because I don't want to deal with NASA. NASA is a huge bureaucratic monstrosity, and so so is ESA. So all these space agency things are just insane. So I would rather build a telescope than send a spacecraft. But if you're forcing me to send a spacecraft, where would I go? I would like a spacecraft that could go to the Kuiper Belt and stay there instead of shooting right through like the Pluto spacecraft shot right
New
through.
Horizons.
New Horizons shot through at 4 kilometers per second. So it's 10 years to design it, 10 years to get the money to do it, 10 years to build it, 10 years to get there. And the people that originally thought of it, half dead by the time it goes through the system. That's just too slow and too long. You got to send a spacecraft out there, and it's got to stay, which means you've got to take some kind of a propulsion system that can stop it at Kuiper Belt distances. And that's the problem, because launching a rocket big enough to stop the forward motion is presently not on the cards. It's something we can do. So it's going to need a nuclear rocket or something that's politically unacceptable to be able to do that. But I would like a spacecraft that goes to the Kuiper Belt and either goes into orbit around a Kuiper Belt object, or better, can go into orbit because it's got its own propulsion system, not ion drive. Ion drive is kind of pathetic. Can jump from object to object. So it can literally visit tens or hundreds of Kuiper Belt objects over the course of a few decades. That would just be awesome. And then we'd understand, you know, what is the nature of the diversity of the Kuiper Belt, because one of the really cool things about Kuiper Belt is not just one kind of thing. There's all sorts of different kinds of object in the Kuiper Belt based on ground-based observations. There are all sorts of different dynamical groups in the Kuiper Belt, the classical ones, the scattered ones, the resonant ones, the detached ones. There's a whole lot of binaries. There's some that are ultra red, there's some that are not. There's just a lot of diversity in the Kuiper Belt. And to try to sample that diversity by sending a spacecraft, ding, 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 then you need many, many spacecraft. It's just not going to happen in my lifetime or anybody's lifetime, I suspect. So I think I would ask some generous donor to give me enough money to build nuclear rockets and launch them to Kuiper Belt distances and do that and send back a lot of data. That would really open that up and make everything a lot more understandable than it presently is.
And we need a spore drive, don't we?
We need a what?
Spore drive. Stannis and his spore drive from Star Trek Discovery.
Oh, I'm afraid I don't know what that is, but sounds like a good thing. Let's get that.
It's very good.
Okay, I'll take two.
Or just an FTL drive, hop into warp space, jump out when you get there and have a bit of fun and look at all the objects.
Yeah, but there's no tardigrade DNA involved in that, so it's no fun.
All right.
Looking very worried.
So I had to get a Star Trek reference in before Nick did.
Yes.
Neil.
Yes, Nick. Well, I was going to ask David, which comet from history, if you had all the technology you got now, you've got the the Hubble Space Telescope, and which comet from history would you like to observe with the Hubble or the technology that you have at your disposal today? If you can go back in time, which one would it be?
I'm thinking.
Okay. It's a tricky question. There's so many.
Yeah, I probably would pick one of those daylight comets. You know, the comets so bright you can see them in daylight, but not when they're that bright, when they're far away.
Yeah.
And I'd like to do with those comets what I'm trying to do with K2, which is follow it and see how the activity develops and figure out why. So, you know, daylight comets, maybe they were just big. That's what many people think. They're just bright because they're big. But we don't know that, actually. There's no strong evidence, to my knowledge, that that's the case. So if you observed them far away from the sun, potentially even before the activity started, then you can estimate the size of the nucleus. And you'd answer that question directly. It's a big one or it's not. And then if it's not, what's going on? Why is it so bright? Is it actually breaking up? It could be that they're super bright because they're crumbling to bits and producing a lot of debris. We don't know. So I would probably pick one of those days, but far away, before or after it became a daylight comet, I think. Yeah, that's my first guess.
Good answer.
It is.
Yeah. Mary?
So have you done some work as well, looking at cometary activity in asteroids? I'm interested in that side of comets as well.
Yeah, so indeed we have. So this started with this thing called an asteroid, which became known as Comet 133P, Elst-Pizarro. So Elst and Pizarro are two like Belgian guys. I think one of them's Belgian, the other is Italian or something. And they were looking at asteroids, and they found what they thought was just a comet. And this is about 1986. So it was advertised, hey, we're looking at asteroids, but we found a comet. Then it turned out that the orbit is entirely asteroidal. It's in the asteroid belt, and if you didn't know it looked like a comet, you'd never say it's anything other than an asteroid. So people thought about that, and it was a big fuss, actually. There was a lot of discussion about it in magazines like Sky and Telescope. and even in the popular press in 1986 and 87. And basically nobody had a good idea for what had happened. So then it fell quiet. Then people stopped talking about it. Nobody else looked at it, it's like, oh, it's gone. And so it just kind of disappeared. Then in the year 2000, a Hungarian guy called Imre Toth wrote a paper saying, well, I've got an idea. It must be two asteroids collided and they made a cloud of dust. And that's what this Pizarro was. That's what they saw. And then again, the deadly silence descends. No discussion, no papers. There was just that one paper written saying it's a collision between two asteroids. So then I thought, well, if that's true, and if I look at it again, it should not be like a comet. Either it's completely smashed itself to bits and there's nothing left, and so I won't see anything, or it'll look like an asteroid because the debris has gone away and just the asteroid survives. But I looked and it was active again. So then I knew there's a story to tell. So something interesting. So that is the first of what we call the active asteroids. And now we have like 30 or something of these bodies. So my student Henry Shea made this into his PhD thesis. So he worked on the first few of these. And we've both continued to work on these objects since then to build the number up to about 30. So really, it's like rubbing salt into a wound. There's this old question of exactly what is a comet compared to an asteroid. How do you know the difference? And what we discovered is that all sorts of people have all sorts of different ideas about what is what and for what reason. So we originally called these objects main belt comets because they're in the main asteroid belt and they look like comets. And to me, that was like, okay, that's the logical name. They're definitely in the main belt and they definitely look like comets. But that pissed off a whole bunch of people who seem to have strong ideas about what a comet is. So then we introduced this term active asteroids, and that pissed off a whole bunch of other people who are very concerned about exactly what an asteroid is. So you can't win at some level, but they are both active asteroids, and they are in some cases main belt comets as well. So some people think a comet is a comet just because it looks fuzzy. So that's the operational definition. You look through a telescope, if it's fuzzy, it's a comet. The trouble with that is, your ability to see the coma depends a lot, as you know, on the observing conditions. Is the sky bright? Is the sky dark? Is your telescope big? Is the telescope small? Is the integration time long? Is the integration time short? So the appearance can depend on the characteristics of the system you use to image the comet. So that's not a hard and fast definition. You can have many objects which look to be point sources like asteroids, but actually they're weakly active comets. So that's not a great definition, but it's an operational definition. Other people think, well, comets are icy, and so if a body has ice in it, then it must be a comet. The trouble is we don't know how to measure what's inside a body. We have no way, in general, to see what's inside a comet, a nucleus or an asteroid or anything. We cannot see inside. We can only see the surface, and if something comes out, we can see it, but otherwise we can't. So that's not a great definition. And then the dynamicists come along and say, oh yeah, the comets form in the cold outer parts of the solar system beyond the snow line, where you can trap water as an ice instead of a gas, whereas the asteroids formed inside the snow line and they're relatively free from water, certainly free from ice. And the trouble is we don't know where anything formed either, except through a dynamical model, and the dynamical models are changing all the time. Everybody has their own favorite dynamical model of everything, as far as I can tell. So there's no really great definition. There are all these different definitions. And so that's been a kind of a sticking point for some people. But what we do know is that these, I'm going to call them active asteroids, these active asteroids are definitely dynamically asteroids. That is, they go around the sun in orbits which are totally like the orbits of other asteroids that are stable for the age of the solar system. They're not on elliptical orbits. They're not substantially perturbed by the giant planets or any planet. They're asteroids, but they do also show comet-like activity sometimes. So we know that for a fact. So in a way, you can call them whatever you want. It's like, is Pluto a planet or not? I don't care. It's up to you. But the deal is, these are asteroids by their dynamics, but they're comets by their appearance, because they're losing mass measurably. So then the question is why? So we found a whole bunch of different things. So we have several examples where two asteroids indeed have collided, and we see the smash, we see the debris. So before we saw these, people didn't even think about seeing that. So oh, the collisions are so rare, we'll never see that. But it turns out they're quite frequent, and we can see them on a roughly annual basis. So we've seen collisions. There are other cases where a body has spun itself up due to a radiation torque called YORP, funny thing, but they're spinning fast and they're throwing off material. And in one case, at least, they're seen breaking apart. The nucleus, the asteroid is breaking into pieces because it's spinning too fast. So we've identified that. There's one object that goes very close to the sun called Phaethon, which is the parent body of the Geminid meteoroid stream. That body releases material at perihelion, probably because it's so hot that the surface is cracking, it's thermally fracturing. And so we've seen thermal fracture as a process for driving the activity. And then indeed we have sublimation. So some of them, about 1/4 of them, are ice sublimators, just like comets. So they're basically literally doing the same thing. And we know that because when they're perihelion, they look fuzzy. And when they go away from perihelion, they don't look fuzzy anymore. So their activity depends on the distance from the sun, which means it depends on the temperature of the body. So we found all these different things, all these different processes can make an asteroid look like a comet sometimes. Some of them are genuine comets in the sense that they're icy, but they also are genuine asteroids in terms of their dynamics. And so that I'm calling the third reservoir. So we have the Oort cloud, the Kuiper belt, and the main belt of the asteroids is the third reservoir. And it turns out when you do the numbers, when you do the statistics, it seems like most objects in the outer asteroid belt could be in this icy category. So it may be that essentially all asteroids in the outer belt are ice-rich bodies, which many people would say are comets. And that's interesting because that part of the asteroid belt is probably where the Earth gets at least some fraction of its water, and the terrestrial planets get their volatiles, other volatiles. A long time ago, so in the beginning of the solar system, that's a relatively convenient, highly efficient place to get water from. So the oceans actually could come from this place in the outer parts of the asteroid belt a long time ago. So the idea there is, that's really interesting. If we could go there and sample the ices in those objects, the active asteroids, then maybe we can learn something about the origin of the oceans and the origin of terrestrial carbon and all those goodies that probably are ingredients for the origin of life. So that's a subject that arose, it started with Els Pizarro in '86, but it really started when we realized that Els Pizarro is just the first example of a whole population of, that we'd never noticed before. That was about 2006. So this whole subject is about 15 years old, something like that. And again, was not predicted or expected. Nobody was thinking, this is what we got to try. It was just kind of a chance thing, just unfolded. Yeah. So indeed, there is this third population of comets in the asteroid belt.
Fascinating.
Interesting. I have one other question. Do you think within the near future we'd be able to find comets in orbit around some exoplanet systems?
Well, oh yeah, that's a good question. So, I mean, some people would say it's already been done. So, for example, Beta Pictoris is this this star that has a disk around it. Now we know it's got planets around it too. For a long time, excuse me, people have been taking spectra of that star. And so you can see, the emission, the profile of the star itself. But you also see absorption lines due to material between us and the star. So normally you'd say, big deal, it's just stuff along the line of sight in the interstellar medium. But these absorption lines in Beta Pictoris move. And so they change their wavelength because of the Doppler effect. And that's due to material falling into the star. So Beta Pictoris has objects around it, which occasionally pass between us and the star. So they make a line, an absorption line. But they're falling into the star, which we can tell from the Doppler shift. So they come and go, because sometimes they're in front of the star and sometimes they're not. But it's accreting things. We don't really know what they are, but the group that studied them the most, which is this group in Paris, believes that they're comets, basically super comets, big comets. And so we're looking through the coma of a big comet that's falling into the star. So that's not impossible. So the claim has been there for about 20 years that that's what we're seeing. And then there are less direct measurements. So these comets are not seen, right? So you don't actually take a picture and see a comet next to the star. It's hopeless to do that because comets are so faint. But you're seeing absorption as the comet goes in front of the star. There are other indirect ways that suggest, yeah, maybe indeed we're seeing comets falling into stars. And there's one other example that actually I would like to mention because it's kind of cool. You know, white dwarfs, these are white dwarves. People used to say dwarves, but now nobody says dwarves, they say dwarfs. So the VES ending is just gone. I don't know what happened to it. The white dwarfs have very strong gravity. So white dwarf has basically the mass of the sun in an object the size of the Earth. So it's 100 times smaller than the sun. It's 1 million times denser, roughly. So it's a very, very high density body. And that means the gravity is really, really high. The gravity in the surface of the white dwarf is like crazy high, 1 million times. That means that the elements in the atmosphere of the white dwarf tend to sink, and the heavier ones sink very fast. So you have an atmosphere as hydrogen, helium, and then all the rest. All the rest sink really quickly. So you end up with an atmosphere dominated by hydrogen and helium, or sometimes just by hydrogen. But even though the time scale for those elements, the heavy ones sinking, is very, very short, it's like 1 million years or something, a big fraction of the white dwarfs are polluted. And so we see absorption lines in the white dwarf from things like iron, silicon, oxygen, aluminum, stuff like that. And those are the things that terrestrial planets are made of. So in fact, the explanation for that seems to be that the white dwarfs are being hit by bodies, unseen bodies from a surrounding disk. And those bodies are dissolving in the atmosphere, and they fill up the atmosphere with what astronomers call metals for a while, for 1 million years or less, and then that stuff sinks down, and then the star becomes bland again, just hydrogen, nothing much going on. And then another body falls in, and it will go back to showing a metal polluted atmosphere for a while. So we see spectroscopic evidence for this stuff falling into the white dwarfs. And that's pretty exciting. It's pretty interesting. And so people have used measurements of those heavy elements in the stars to calculate the compositions of the things that are falling into the white dwarf atmospheres. And indeed, they find compositions kind of like the Earth, kind of like even different, very specific kinds of meteorites. They've been identified. Even bodies with an ice content, so icy asteroids or maybe comets. People have done a whole lot of work on the last 10 years, something like that, to see what is the composition of the stuff falling into the white dwarf. And there seems to be no other good explanation for why you would have these heavily polluted white dwarf atmospheres. It seems to be that's what you got. It's macroscopic bodies. They're hundreds of kilometers sized asteroids that are falling into these white dwarf atmospheres and dissolving.
Wow.
So that's another answer.
Amazing.
Yeah.
I'd somehow missed all of that stuff, so I need to go and dig out
Well,
some.
it's relatively
papers.
new. relatively new, and actually not many people are doing that for reasons which are slightly mysterious. Like normally astronomers copy each other. So if something good comes along, everybody copies everybody else, and they pretend, oh, I'm doing it for the first time, but it's not really the first. But for some reason that hasn't happened with this polluted white dwarf business. There are only a few people, maybe 10, working on that.
Wow.
So it hasn't really exploded. And so perhaps that's why you haven't heard about that.
I think it will eventually. It's really interesting.
I
think so.
I think I'll have to go find some of the papers and print them out and take them to work to read. And definitely shock everybody.
It's cool.
Neil?
Mark, talking about the interstellar things, there's a theory that there could be up to 19 objects that has been captured by Jupiter. Do you think that may be the case? We have some in orbit around Jupiter?
No, I don't think so. I never understood that paper. So the deal is, if you're coming in to the solar system at very high speed, which basically by definition these objects are, then the probability of capture is negligible. I just don't see how you can capture any of them. I mean, the whole point is they can't be captured. They're going too fast. They're going faster than the escape speed. It's like, if I throw a donut, you can catch the donut. But if I shoot you with a bullet, you can't catch the bullet.
True.
It's basically like that.
Yeah.
Maybe I'm wrong, but I simply didn't understand that claim at all. It could be correct. I recommend you find that person and talk to them.
Surely the sun is more of a candidate for capturing it if it was going to be gravitationally attracted to something.
But the sun, how's the sun going to do it? So to slow something down, you need friction.
Of course, yeah.
And there's no friction. The solar system is empty. There's no friction. I mean, it could hit something, but the probability of hitting something is like close to zero. So there's no friction. So capture is really, really hard for that reason. There's no way to slow something down because space is a vacuum. It just goes, that's it. Yeah. Maybe I'll read that paper again, but I just didn't. I just thought, what is this?
Mary, any questions?
No, I've asked loads. I've hogged him slightly. Sorry, David.
Neil?
I was going to mention this because one of the most interesting papers I've ever read that you've written is the one about Swift-Tuttle and why it hasn't been seen for such a big comet. And it's only been recorded in history a couple of times. And I just wondered if you could elaborate on why such a big comet should be seen and hasn't been seen in history.
Actually, to tell you the truth, I can't. I have no memory of that. I know I wrote a paper about Swift-Tuttle, but I don't know what that said at all. It was a long time ago. 1996, apparently. Yeah,
it's a great paper. Yeah.
It may be, I don't know, but it's like somebody else's paper. I mean, I had a postdoc actually a few years ago who systematically went through all the papers I ever wrote from the beginning. And then came to ask me questions about each one of them one by one. And it was excruciating because I just don't remember, like stuff 4 years ago. I wrote 40 to go read a paper again. And he looked at me like, did you actually write these papers in the first place? How come you don't know what's in them? So I felt like a fake. That's how I feel with this Swift-Tuttle.
If you write one paper, you remember it, but once you've done quite a few over a number of years, it's the same with any articles I write. 2 weeks later, I have to go back and open it in Word to remember anything that I've written. So,
really, And also writing a paper, I have to say, is for me, such a painful, traumatic thing that once it's done, I want to forget it. I want to move on. I don't want to look back at it. I want to just do something else. So the truth is, I can't answer that question. But this is an observation with the radio telescope. I haven't done any of that for decades. So, if I read it, I could answer your question, but there's no time.
Well, I think probably the best thing to do right now is to thank you for coming on, David. We hope you'll come back at a later date because looking at the clock on the computer, we've been going for an hour and 25 minutes with
Ooh,
you alone.
ooh, sorry.
So it's been quite a good show. So I think I'm going to say thank you for coming on, and have a good afternoon where you are.
Okay.
Yes.
And
Thank you, David.
thank you. Yes.
And thank you, and
welcome.
don't apologise. The longest Comet Watch was like 3.5 hours or something, so
Oh my God.
Yes.
it's not a problem.
No, it's been
That sounds
brilliant.
brutal.
And also, I wanted to say thank you as well for the memory. I was reading on your Wikipedia page that you used to use a mobile library for reading material when you was younger, and that's just such a vivid memory for me as a child. And I just don't even know if those things still exist now. But yeah, the big yellow library bus, it was amazing.
Did you have any books in your house?
Oh, we had a lot of books in the house as well, but never enough. So
we didn't. So those were the books. For me, that was books. It was like is in the back of a van. I thought it was really cool.
Yeah.
I think there's still a few of them in existence over here in the UK, and I know that quite a few have appeared in the States again. In the last, I want to say, my recollection, one was in upstate New York. That would have been 10 years ago, perhaps.
Really?
Yeah. So they're still there somewhere.
Okay.
We have one.
I think that's good.
Yeah. Right. I think probably the best thing to do is to wrap the show. Thank you for coming, David.
Thank you.
Thanks for asking me. Thank you.
It's great.